One of the most important things we need to know about as a physicist or an engineer is uncertainties. Pretty much any measurement you want to make is going to be uncertain. Now this is a bit unfamiliar from school. At school you often have to give exact answers. But in the real world that's not the case. Most measurements that matter, there is no exact answer. There is only an approximate answer and an uncertainty. And no matter how good you get, you're never going to get the right answer. You just get the uncertainty smaller and smaller, but it never goes away. Now that's not always true. There can be absolutely right, precise answers if you're after an integer. For example, how many elephants are there in this room? I can tell you precisely 0, not 0.01. But most real situations, you're going to measure a continuous variable like a length or a weight. And for those, then the answer is always a bit uncertain. Now, why is it uncertain? Why can't you just measure something exactly right? Mathematicians in particular find this deeply offending. We mathematicians like exactly right answers. Why are all these wishy-washy physicists and engineers having uncertainties? Ugh. Well, some people think it's because we make mistakes, errors. And indeed, we are humans, and generally speaking, we make errors. We can write down the wrong number, stuff up our experiment. But that's not the normal cause for the uncertainties you worry about. Because normally you can catch those errors if you put some checking and be careful, get two people to double check your results, check the plausibility, monitor them as they go. That are all the techniques we'll teach you in this course for spotting human error. But even without human error, there's going to be a problem. Now the first problem you encounter when you try and measure something more accurately is your measurement equipment. For example, let's say you're trying to measure length. You might be using something like this, a ruler. And for a ruler like this, the marks are about a millimetre apart. So you're not going to be able to measure distances to much less than a millimetre. Some people are optimistic and say they can get to your 0.2 or 3 of a millimetre. I'm a bit more pessimistic about these things. Likewise, if you're trying to measure voltage, you might use a multimeter, and this is going to tell you it to 2 decimal places, not 5 decimal places. So that's the first cause for uncertainty, crap equipment. And you can solve this one by buying more expensive equipment. So for example, you could measure length with a set of vernier calipers rather than with a ruler, and that will get you accuracy of 1/10 of a millimetre easy. Or you could use a laser interferometer, which might get you down to below a micrometre accuracy. The trouble is, you can usually get better equipment and measure things more accurately, but it's going to cost you money. So there's always a trade-off. You have to ask yourself, how accurate does the answer need to be? Can I justify spending like $1 million to measure the length to a nanometer? I mean, if, for example, you're trying to measure, say you've got a primary school running carnival and you want to map out the 100-metre track, does it matter if you're a centimetre out? No, it doesn't. For the Olympics, it probably does matter. But would it matter if you were a micrometre out? No, it wouldn't. On the other hand, if you're trying to measure gravity waves, that is absolute death. You have to be able to measure the length to an accuracy of 10 to the minus 20 of a metre, which is why it costs hundreds of millions of dollars. So it all depends what you're trying to do, and you can get more expensive equipment. However, even if you have expensive equipment, there are still uncertainties. You can buy the most expensive equipment in the world and it won't help you get to 0 accuracy. One reason is what are called systematic errors. A systematic error is something that you have not factored into your calculation. So say, for example, I'm measuring length off with this ruler here. The ruler will change its length depending on the temperature. This is wood, and it will absorb moisture, and as temperature increases or decreases, it will expand and shrink. So if the accuracy really mattered to me, I would have to calibrate this at a fixed temperature, maybe make all measurements at 20 degrees centigrade, or maybe I could get a calibration chart and calculate the length of this against a function of temperature. So when it's 24 degrees, it might measure lengths 1% too low, or something like that. So there are always things that you have not factored in, like, for example, how is it going to vary depending on temperature? How is it going to vary depending on humidity? And you can factor those in and get a more accurate answer, but it costs you time and trouble. So systematic errors are actually a good thing in some ways, because when you're up against systematic errors, you know you can do better by taking more care, by looking at all the things that could go wrong and correcting for them. So that's often a good way to find an interesting scientific research project. If what's stopping you is systematic errors, then you've got a job cut out. Work out what all the systematic errors are and narrow them down and get rid of them. This, for example, is how the Japanese car industry took over much of the world in the 1960s. They became able to manufacture car components to much higher precision than the American and British manufacturers. And basically it was a question of, why is our door, half a millimetre too big? What went wrong? Was it the change in the temperature? Was it a change in the lathe? Was there some vibration? And a whole bunch of engineers worked slowly and carefully through all the systematic errors and got rid of them. It's also, for example, how we discovered planets around other stars as astronomers. You're trying to measure the motion of a star caused by a planet orbiting it to an accuracy of only centimetres per second for something that's a light years away. And there were all sorts of things that went wrong. The spectrograph would flex and bend and the atmosphere would distort the light coming into it. But slowly, over many, many years, people found ways to measure and correct all these systematic errors and eventually got down to the precision enough where they could start finding planets.